Welcome to part 2 of the ESTeem radio modem training class. In day 1, or part 1, what we actually covered was the basics of radio communication. We went through antennas, we went through coax cables, and what it actually took to calculate how the radios how much energy is put into the air so we can make some of these calculations that we're going to go over through this section. When we're talking about making a successful RF network, it is actually a three-step process. The first step is where we use a math model calculation to figure out, is the hardware that we are proposing to operate within the system going to be able to provide us the bandwidth or the amount of throughput that's necessary for the application. The next step is going to actually be a physical testing of that. What we're doing is really we are confirming the results that we find during the math model analysis. Things happen during the site survey that we have to be able to make adjustments to the system. Things that we don't necessarily see when we're doing the RF system design. Buildings, trees, overhead power lines. These are the things that we have to be able to measure and make adjustments to our system design for the overall network. The final step of this is actually what we call the site commissioning. Now, as far as testing goes, we perform the exact same testing that we do during the on-site radio survey. The only difference is that we are actually testing the installed hardware. Now, this seems like a tremendous amount of work to get a system to operate. But again, what we need to do is we need to understand what we're actually building here. We're building the infrastructure for all communication that goes on between different devices within this network. If we have a poor communication link within the network, every device that is connected to that communication link is going to have a problem with communication. So we need to make this as the most reliable we possibly can do. The one thing that we need to understand is that each radio application is unique. Every one of them is different. Wireless is actually being applied in many different applications now, everything from your cellular phone, handhelds, tablets, Wi-Fi in your house. But very few people have a good working knowledge of what's going on in the background. In other words, how do we design to make a very successful wireless system? The other thing that can be very confusing is, quite honestly, there are many different vendor specifications out there, and you're seeing a tremendous amount of different information in those. For example, you may see some that have a 2.4 gigahertz radio that'll say it goes 30 miles, and some that'll say they have a 2.4 gigahertz radio that'll go 5 miles. And looking at the specifications, they look very similar. So what is the difference? How does some of them go longer distance? Some of them go shorter distance. That is one of the key elements that this tool will actually allow you to do, is actually review these specifications and see honestly where these actually came from. So what we're talking about here, this first phase, is just a simple math modeled program that allows us to calculate what's called a path loss, or a path loss calculator. The nice part about this path loss calculator, it assumes worst case conditions on everything. And what I mean by that is what you'll find is that the installed hardware will generally have a higher signal strength than what we actually calculate. So overall, this model is fairly conservative. So it does start us in a good point. In other words, we're not looking at the best case conditions and then trying to apply those in a real world. We're actually looking at one of the worst case conditions, and the real world tends to be a little bit better. Another key benefit of being able to do the RF design program is this allows for modifications to the system's design prior to any installations or purchasing of the hardware. If we find that we can change antenna types, we can change coax cable types or cable lengths to make adjustments within the system, and at this point it costs nothing. So it's very, very expensive to make these design changes once they're installed out in the field. The next thing this program allows us to do, it allows us to provide us a means of determining what we can expect as far as data errors. Now, one thing we need to understand is that wireless communication, it's an imperfect world. So there are going to be times when the information gets sent out between the radio and the opposite side, either through noise or just missing the packet entirely, isn't going to get through. The radios themselves have a means of finding this out and through a back and forth transaction to where they are actually can retry. So one thing to consider it is that just because a system or a radio goes out and has a few retries does not mean that we're talking about a failure. So for example, if a radio basically sends the communication out, it doesn't get there, it sends it the second time, it gets through. It sends it the next packet, it doesn't get there, it sends it through the next time, and it gets through. We'd consider that 100% retries. Now, it's very inefficient to do that, but the data is still going to get through 100% of the time. So what this RF design program does is it gives us a means of determining what we can expect as far as those number of data errors. Okay? So we actually do have two different RF design programs available. The reason for that is the Horizon series of radios that we manufacture has a variable data rate, okay, based upon the received signal strength that they have, the hardware that's put into those. Each one of those will actually have a different data rate based upon a given distance. So this program actually takes and models that and will tell you, based upon the hardware that we select and the distance within that application, what we can expect as far as the data rate without having to calculate each one of those one by one. For example, the Edge 900, the Model 210, and the Model 195 narrowband radios have a single RF data rate. So they use a different calculation program because you just enter in the information for each end and it's going to give you whether it's good or bad because there is no variability as far as the actual speed that the communication goes through. We'll see in a couple slides here what we're actually talking about when we actually get into the Horizon series. So to continue on with what we covered in the first training session, we're going to now cover a few more network or RF design terminology. The first one we need to understand is when we're talking about line of sight. Okay? The line of sight is a critical element to all the frequencies that we are dealing with here, especially any frequency above 900 megahertz. Line of sight between the antenna becomes very critical. Now, this is maybe an oversimplification of the Earth horizon, but to be honest with you, the radio horizon actually comes up quite faster than you would ever expect. For example, if you're 20 feet above the Earth surface, the furthest that you can see before you actually strike the Earth's surface is about 7.62 miles. So it actually will affect longer distance applications. So part of the RF design program will tell you that the minimum height that's required to break the curvature of the Earth. Now, of course, this curvature of the Earth doesn't compensate for hills and valleys and everything to it. This will actually model only perfectly like this over water is really the only place that it models perfectly like a sphere. But it will give you an idea of these are the concerns when we're doing it in the design phase. Because again, what we're trying to do is we're trying to eliminate out the problems in the RF design before it gets installed in the field. So we may end up somewhat over designing the system, but at this point, that's what we want to do. We want to go in with our best foot forward. So when we're talking about this, what we're talking about is a reference line for height clearance is the bottom of the antenna. So a directional Yagi type antenna would be what we see here on the left, to where we're talking about the longest of those two rods. Same thing here for the base of the omnidirectional antenna. That's what we're going to consider the bottom, not necessarily the bottom of the pole or the mounting structure that they're actually mounted to. Another new term that we need to be familiar with is this term called a Fresnel zone. And what a Fresnel zone is looking at how two radio patterns or two energy patterns that are created primarily by directional antennas, but even in an omnidirectional antenna, if you look at the primary element of where those two antennas or two power levels go, it actually creates this ellipsoid as we see here on this graphic. An ellipsoid is kind of shaped like a football. Now what actually happens is that just as we were talking about in the first training session, The one thing that is most destructive as far as RF energy is this principle called multipathing. Multipathing means that as the RF signal travels past an antenna, what it will actually do, if it strikes a surface, it can actually reflect back, and as it arrives at this antenna, once again, it actually can arrive out of phase from timing and cancel the original signal out. Now, the one thing that we need to be concerned with is as we start using higher and higher frequencies, we also can potentially have this principle apply to anything that gets within the same pattern, but not necessarily coming from behind it, but actually when it's transmitting, it can come in, strike that surface, and then arrive out of phase at the antenna from anything within this, we'll call this dead zone. Okay, so we not only need to consider directly having the line of sight, but we also need to be able to measure anything that is within the first 60%, that is the highest reaction zone of that Fresnel zone. Now the Fresnel zone is actually calculated because it's actually based upon the frequency of operation and the distance. So part of that RF design program will tell you the height of the Fresnel zone at different locations. So when we go through that RF design program, I'll show you where that's actually calculated. Primarily what we're talking about here is this is going to only really happen on frequencies 900 megahertz and above. Now putting all this together, we've used this terminology of effective radiated power and how we do the calculations. Really, this is what the path loss calculation program measures. What we actually do is we take the RF power that is created at one antenna. We essentially take signal loss all the way up until we hit the antenna. So this is going to be the feed line loss. We then go into and look at the gain of the antenna. Therefore, we know how much energy is being put into the air. That's going to be the effective radiated power. That's the transmit side of this. At the opposite side, we know how much spreading loss there is because that is actually controlled by nature and it's a function of the frequency and the distance between the transmitters. So at the opposite side, we now have a received signal that has come through the air. But we also need to process it in the exact same way at the opposite end. So we have our received signal coming into the antenna. We get the same benefits of gain on the receiving antenna that we received on the front end. So that antenna gets boosted up in the same way. Then we actually take a signal loss all the way down the system until we arrive at the opposite radio. Therefore, we can make these calculations throughout the entire system. Because of that, now we have the ability where we can make a math model analysis based upon the hardware that is within the system. Okay? The next step that we'll take a look at is another term, which is what we call a fade margin. Really, and what a fade margin is, it's the difference between the minimum value that we need as far as the receiver sensitivity versus what we're going to calculate as far as the received signal strength we expect between the two. If you think of it, this really is essentially an over design of the RF system. Okay? The fade margin is actually calculated in the same decibels at the same amount of the received signal. The fade margin, if you think about this, makes sense. It's actually going to be controlled by all elements of the antenna system. If we increase the transmit power, our fade margin will go up. If the feed line gets extended or you change to a different type, we can actually add more attenuation, so this fade margin goes down. The receiving or the transmit antenna, if it has a higher gain, your fade margin will go up. Same thing on the receive side, the antenna gain, feed line attenuation, receiver sensitivity. Each one of these elements will affect the fade margin. Well, a very good question to ask at this point is, who cares? What do we need this fade margin for? The big thing is we need to understand that we're putting this into an imperfect world, and things are going to be constantly changing. Equipment ages, whether it be in the antenna, the coax, or the hardware itself. So what will happen is that you will over time not get as much signal as you had when it was first installed. The next thing is antennas will naturally go out of alignment to a certain extent. So they will happen because they're based in weather. There will also be more unexpected man-made noise or more interference by other transmitters coming into the area. So one thing to keep in mind, if we design an RF system that will set up to work now, in other words, we set it up to where there is no fade margin, the one thing I can promise you is that it will fail in the future. So how much fade margin do we actually need? This comes back to what we can expect as far as retries. So for a digital transceiver, kind of a basic rule is, if we give ourselves 10 dB of fade margin, then we can expect 10% link retries. So 1 out of every 10 transmission that goes through is going to be lost because of noise or interference or something like this, and the transmitter will have to resend it. Again, we're still getting 100% reliability, but we're losing a little efficiency. What happens is, as we increase this fade margin, the percentages of that actually start dropping dramatically. We give ourselves 20 dB of fade margin, we can expect a 1% link retry. We give ourselves 30 dB, it drops all the way to 0.1% retry. So what we have done within this RF design program is said that anything that is over 10 dB will show up on the screen visually as a green link or a good link. Anything between 1 and 10 dB of fade margin will show up as yellow, or we consider that marginal, or anything that's less than 1, essentially we show it as red, so that we know that there is a problem and changes need to be made when we're designing the system out. Okay. How do we start? Where do we start with all this? Now that we've gathered all this information, we've gathered all this knowledge, we're now going to start applying this to an actual working system, and we'll start seeing where all the things that we learned as far as the antennas, the cables, the gains, the losses, the Fresnel zone, all of this will start playing into actual site work. Again, this is going to be the first phase of what we do when we do an RF system design. We're going to look and see, based upon the hardware that we select, is it going to provide us as much bandwidth as we expect? So the first thing we need to do is we simply just need to find out what is the distance between the locations. And what we're talking about here is a line of sight distance. Now, what happens is that if we don't have a line of sight between the antennas, it doesn't necessarily mean they will not work. What it tells us, though, is that at that point, we cannot make a reliable prediction on what's going to happen between those 2 points. So everything that we do as far as the design is based upon this line of sight. I just wanted to put that out there first. So we can simply just start with a simple network layout. You can draw this on a piece of paper. This does not have to be very complicated layout. What we're doing, though, is we need to find the distance between all the points. So you can do that either through calculations on a site map. If you know the longitude and latitude between those, the RF design program actually has a tab in there that will tell you can put in the longitude and latitude between 2 points, and it will give you the actual distance between those 2 locations. You can use a handheld GPS. We've actually used those for years in doing site surveys, that we mark the points and it'll tell you the distance between it. But one of the best friends that's come about is, it started out as kind of a neat little tool, but has become a very, very powerful tool when doing the RF design, and that's Google Earth. It's a free download utility. The best part is you can visually look at it, and I've got a few examples of actually how that helps here on the next couple slides. So once we've started with our initial sketch, the system overall, we need to understand in a fixed point system, we may have many different types. We may have a base, we may have a repeater, we have multiple remotes. But no matter how you look at that, really what we're talking about is multiple, essentially point-to-point locations. Whether we're talking from the base to the repeater to the remote, the repeater to another repeater, each one of those needs to be evaluated. Each one of those is considered an RF path, and we'll calculate each one of those links separately. Let's go ahead and start with a very simple site sketch. This could be anything from a water system to a mine application. What we're going to start with, though, is a master location and 4 remote locations we want to talk to. Because of the terrain and the environment that this goes into, we have a very good line of sight to 3 of the sites, and one of them that sits on top of this hill is actually going to need to act as a repeater for this remote location, because we see here we have no line of sight direct to it, or we have no line of sight over here from this remote. So we're going to do our calculations first here, then to the remote over here, and then we'll take a look actually at the site to the repeater and to the remote. All points within the system will start with this calculation. So what do we need? Where do we start? Once we've got the distance, the next thing we'll take a look at is actually height and elevation above sea level. That is going to give us a good reference point. Again, we can go back to the reference maps, handheld GPS, or Google Earth itself will actually tell you the height of a location above sea level. What we're trying to do is we're trying to estimate the installed antenna height at each location above the ground level to achieve a line of sight to the destination. So it may need to be on top of a water tank. It may need to be on top of a tower, on top of a building to get a line of sight to where it's going to. That height above the ground is the ultimate height that we need to know. We also then can estimate from that height what type of coax cable, if the system is using coax, from the antenna to the equipment cabinet. We're going to need that information to put that into our calculations to see how much signal loss is going to actually be within the network. As I mentioned to you before, Google Earth has actually done a tremendous amount of work that used to take several different programs. The first thing it does is it actually gives you a fairly accurate site location. You've got a visual top-down view of it. When you're looking at locations that, normally it'd be very difficult to pinpoint on a map, to be able to see the building that you're talking to, or the tower, or the location that we're going to, you can get very accurate within that. It gives you the longitude and latitude for that site. It gives you the distance between points when you actually draw a line between there. One of the best things that it has brought out, it allows you to actually look at a side profile, as you see here in these two graphics. You draw a line between any 2 points within Google Earth, it'll actually give you a side profile. So what it does is this would be, say, the starting point at one side. This would be the ending point within that link. So we can see here we have a tremendous amount of hills in between there. This would be kind of a comparison, this bottom one. So we've got height here, we've got this height here. As long as we have a fairly decent height of our transmit over here, you can see that we can actually get a line of sight out here to the remote. That's really the benefit of being able to look at this side profile. And again, this all comes through Google Earth for no cost. When we're talking about height above sea level, or height above the ground at any location, what I'm making reference to is if we take a look at the antenna height to get the line of sight, this is going to give us the height, the length of the cable into the control cabinet, or we have, as an alternative to that, we have the ability to pole mount it, which I'll cover here, the differences here in a couple slides. We're still trying to gather all the information we need to make this calculation. The difficult thing to understand is that a height above sea level does not mean that that location is sitting at 500 feet above sea level. It doesn't mean that that point is 500 feet above the ground around it. What it does is it tells us, it gives us a good starting point, because what we need to calculate over here is what we call the adjusted antenna height. So what we're going to do, just the easiest way to consider this is, let's take our site test or site system that we had laid out before. We've got a control room at 560 feet, pump site number 1 at 570, pump site 2 at 820. Our water tank, which is on top of that hill, is at 1,100 feet, and our pump site number 3 is at 480. So the easiest way that we make this calculation is we find out what is the lowest point within the system, which at this point is 480, and then we take that 480 and we subtract 480 from all the points within the system. This is going to give us what we call an elevation differential. We're resetting the sea level to the lowest location because we need to know how high the locations are from each other, not from sea level. We then add to that the antenna height at each of those locations to give us our adjusted antenna height. So we have a 20-foot height at the control room. It's 80 foot above pump site number 3, so its adjusted antenna height would be 100. We make that same calculation for all the remotes. And of course, 15 foot is all we need to get a line of sight up to this water tank. So our adjusted antenna height for pump site number 3 is going to be 15 feet. Now, from this same adjusted antenna height, we can make a calculation on how much cable we're going to need at each one of those. So if we're going to be running coax at each one of these, for 20 feet, we need approximately 30 feet of coax cable. Same thing all the way through until we're down here at the end. So we just rounded up 15 to 30 just so that we've got a good starting point. Now that we have our adjusted antenna height for each one of those locations and the feed line lengths, we can also go back to, like we had covered in the first one, what type of antennas do we need? We know that all the points that are going to communicate to more than one site need to use an omnidirectional. So our control room, which is down here, and our water tank, which is going to act as the repeater, those 2 points are going to be our omnidirectional antennas. Any site that is not an omnidirectional antenna, we recommend putting a directional antenna into it. Not only are we increasing the actual signal strength between the two, therefore increasing the fade margin, but a directional antenna gets you 2 benefits. Not only does it increase the signal strength going one direction, but it also helps eliminate what that radio can hear from information coming into the backside. So it is actually a 2-benefit system. The next thing we'll do for our calculation here is we just need to start with what kind of radio we're going to be dealing with. In a lot of cases, the application itself will dictate what type of radio system you'll use. So for our example here, we're actually going to be using our Horizon Model 2.4, which works in the 2.4 gigahertz frequency range. We're going to use the site information from the table that we just created. We're going to use the vendor information on the received as far as what's available for the antenna gain, the cable loss, everything to this. The RF design program will provide all this information for ESTeem recommended hardware. This tool does not necessarily only need to be used, or it's not locked down to our type of hardware. It is just a simple path loss calculation. So it could be used for any different vendor, but ours, we try to provide the information right in front of you. We then take that information and enter that into what's called the data entry keyboard to come up with the results for what we expect in the RF design program. There are 2 different ways that we could mount the Horizon 2.4. We could use what we call a standard enclosure mount, to where the radio is actually mounted inside of the control cabinet. We then have a antenna that runs into a lightning arrestor. We have a length of coax cable up to our antenna. Now, keeping in mind that all the cable that we have from the radio to the antenna is going to be taking signal loss, that really puts us to the primary reason on our higher frequency radios, we do what we call an outdoor pole mount. What we're doing is we're trying to minimize the loss in the coax cable. We're trying to put the maximum power out of that radio, either directly to it with direct mounted antennas, or with antennas that already have a small little jumper piece to it. So the beautiful part is that when we do this RF design calculations, we can calculate it either way. So the 30-foot cable that we calculated was necessary for the 20-foot antenna heights. In a pole mount application, that cable is actually Ethernet. The beautiful part of that is that we can actually run that Ethernet cable anywhere up to 300 feet away from the equipment that it's actually being hooked into, and it has the same amount of loss as far as the radio is concerned. It will not affect how much energy is being put into the air, so it's a much more efficient way to do it. The other benefits that we get out of using this pole mount kit is we're removing the coax cable, so you get the savings in the coax cable, so we have a lower loss. We also need no particular RF lightning arresters. We also need no specific enclosure. The radio, the only hardware that's necessary for the RF to hook into the control system is the surge protector and the PoE injector, or it can be run through a PoE switch. So we can actually get quite a bit of savings in this outdoor mounting. We'll see how it affects the overall system design though. That's where it's primarily going to come from. Another thing that we need to consider here is the fact that one phenomenon that occurs, and the reason I want to bring this up is when you put in the RF design program, you'll see here that the power levels don't necessarily line up with what you expect to see as far as the specifications. The specifications are all written around what's called a peak power. That's how much energy that radio can actually transmit. Now, what happens is as the particular type of modulation that allows us to go high speed, that OFDM, or that orthogonal frequency division multiplexing, what happens is that as the radio increases in throughput, what happens, the average power level is actually decreased. The peaks within those are the same, but the average power level is overall decreased. This happens on all OFDM transmitter. This is not a bug in our radios, but what we do when we design the RF system, we design it based upon the average power level, not the peak power level. If you design it based upon a peak power level, then your calculations can be off as far as fourfold. So it'll make a lot more sense when we actually see those calculations. So the first thing we're going to take a look at is, let's look at the very first link within the system. The first link is actually going to be from the control room out to pump site number 1. Our height at this site, adjusted antenna height being 100 feet at the control room. Pump site 1 adjusted antenna height is 110. The feed line is 30 feet. But again, because we're going to be using the pole mount configuration, the feed line is actually going to be Ethernet, so that does not apply to our calculations. It makes it very simple. The only thing we need to know is we need to go from an omnidirectional antenna to a directional. What I'm going to do is actually going to swap over the screen here to the actual RF design program. As you can see here on the screen, the RF design is actually a template that is actually built within Microsoft Excel. The reason that we've done this allows us to actually allow the program to do the calculations in a very straightforward manner, so that we don't have to write an application to itself and try to get it to install on different programs. This is actually a very, very clean tool on how to do it. The different elements for this is, we see here, this upper half area is actually the result of what we can expect. This lower half here is what we call the data entry keyboard. From that, we also have, this gives us the idea of what hardware is available. Let's go ahead and start here. If we select the frequency band, as you see here, again, this is the Horizon Series radio tool. It allows us to pick anywhere between 900, 2.4, 4.9, and 5.8. If we select 2.4 gigahertz, which is the Horizon 2.4 that we're going to be operating on, what we can then do is go down to where it says select recommended ESTeem products. We select a Horizon 2.4. We'll run at a standard bandwidth at 20 megahertz, at least to start with. And what it'll do is it'll fill out the information for the different antennas that we have available for that particular radio, and also some information as far as the data rates. This does not cover all the available data rates, but it does give a very broad sampling of the different data rates that are available. So as you can see here, as this radio increases as far as speed, the output power actually can dramatically change. So at the lower data rates, say at 1 megabit, the peak power and the average power are the same. So we can calculate it at 1 watt. If we go all the way up to 72 megabits per second, the RF actual average power level decreases down to about a half of watt. This program automatically calculates these dynamically as it goes there, because what we're trying to see here is this key area right here in the center. This is going to tell us not only the RF data rate, but what we can expect as far as a comparable throughput data rate. What I mean by that is the RF data rate is how quickly the information is being processed between the two radios. there is a tremendous amount of overhead that has to happen. We have security, we have the turning on, turning off of the radio transmitter. By the time that you take all that overhead off, a good rule of thumb for any radio system is about a 2-for-1 split. So whatever you're getting as far as an RF data rate, you can expect about half of that as far as the throughput. And this is comparable if it were going to be setting side by side with a copper connection, a fiber connection. So we're trying to be as straightforward as we can with this. So if you're running at 72.2 megabits per second as far as the RF data rate, a comparable Ethernet copper data rate would be about 36.1. So what we'll do then is this will allow us, if we've calculated that the RF data rate is actually running at 72 megabits per second, the equipment load that we're putting on that link cannot exceed the actual throughput rate. Therefore, you will not over design, or I should say you won't under design what you can expect to happen within that connection. What this also allows us to do is, as you notice here, this gives us all the different gains for the different antenna types that we have available for those given transmitters and what type of antennas they are, either an omnidirectional or a directional, and those given gains. So let's go ahead again and work with this very first link. So the first link we're going to take a look at is from the control room out to pump site number 1. So we know between those 2 points we have an antenna height, the control room at 100 feet, the pump site number 1 at 110, and we're going from an omnidirectional to a directional. So that should give us enough information to do the calculations on this first link. Let's go ahead and we'll then name the site control room. We'll put in there 100 feet, and then this will be pump 1, and it'll be at 110 feet. The distance between those two is actually going to be 4 miles. And I've already put in here the project named training class. To be honest with you, this will not affect anything as far as the calculations, but when you do print this out, or you can save it as a PDF, that will actually be the title that it is actually saved with. We can actually use this in either imperial units or metric units. Either one of those do work. Now, what we need to look at is, we know from the control room we're going to be going from an omnidirectional at one side to a directional at the opposite. So where do we start? What's the best thing we can start with? Well, at this point, we really don't know. So we'll go ahead and start with an omnidirectional antenna. So we see here we've got a direct mount omnidirectional antenna or an external mount. Well, let's go ahead and just make the calculations of the external mount to start with and see how that looks. So we put in the information. So we put in 6 dB. So we enter that in here. We look across this. This tells us that this particular type of antenna, the 20EG, actually has 12 inches of LMR 195. So what we actually put in there is we put in 1 foot, and then you use the little drop down arrow. You can pick multiple cable types. Okay. We cover just about every available cable type that's on the market, at least as far as a standard type. LMR cable, which is a times microwave cable, RG8 cable, which is generally made by Belden, or even the Andrews Helix cables are listed here. If it's not listed within that, one of these is going to get you very close to it. So we do know that we are dealing with a 1 foot of LMR 195 at one side. At the opposite side, we really don't know what kind of directional antenna we need. So let's go ahead and start with the AA203EG. We enter in this information. It's a directional. It's a 6 dB gain here. We then look across this chart here, and this tells us that particular antenna has 3 feet of LMR 195. So we enter in this information, 3 feet, 6 dB gain, 3 foot cable, LMR 195. Then we look up here at this top part, and what this is telling us then, what we can expect out of this RF link. As you notice here, we are color-coded the fade margins based upon the hardware that you select, whether it be a control hardware, a computer. This may be satisfactory, but we don't really know. It depends upon what the load is for that application. If it's a multiple camera application, this may not nearly be enough bandwidth. So the next thing that we can take a look at is what effect does the different type of antennas that we can put in there. As you can see from the screen here, once we've entered the information as far as the omnidirectional antenna, and again, we've got two different types of omnidirectional antennas. We could go with an external omnidirectional antenna, which has a cable to it, or we can actually do the measurement with a direct mount antenna. The thing is that if we use the direct mount antenna, which we see here has a 5 dB gain, our antenna length, we can actually set that to 0. So it'll give us a little bit more information. And based upon these calculations, if we go up here to this upper half, we can see here that because of the equipment that we have selected, we can expect on this link to get about 21.7 megabits per second as far as the RF data rate, which will then give us a throughput of about 10.9 megabits per second. Is that going to provide us enough data rate for the application that we've put in there? It really depends upon the hardware that we've selected. If you're using multiple cameras for this application, 10 megabits might not be enough. So what are some of the adjustments that we can make? Well, we can change antenna types, we can change different cables, we can look at different options as far as what goes on between the system. But let's take a look, let's go back to the slides, and from there, let's go ahead and see what our different options actually are. So what the slides are, this is actually a screenshot from the same information that we entered in before. Again, this is identical as far as the actual antenna type that we've used. The idea behind this is that if you'll notice there that anything that's basically a positive fade margin will show up in green, anything that ends up as a negative will show up in red. So it's easy to identify what are the color combinations going to be. So again, we enter this information. What this will tell us then, we can expect on this rate to be 21.7 megabits per second or a maximum throughput possibility of 10.9. Now, the actual RF data rate could be higher because the radio itself is going to go the highest possible data rate. But for our calculation purposes, these are the numbers that we want to work with. We're trying to be as conservative as we possibly can. The next thing that we want to be concerned with is we'll take a look at what are some of the possibilities as far as changing the antenna type. Well, let's go ahead and see how much effect this actually has. We then will enter in the information we'll keep our base antenna here at 5 dB, but what is the effect of actually changing, say, the remote antenna to a higher gain? So what we then can do is 6 dB the highest gain antenna we have? Well, based upon the type of antenna, the highest gain antenna that we have available is actually our AA204EG. So if we take and look at that, that gives us actually a 19 dB of gain, and it has a 16-inch or a 1.5 foot long LMR 185. So let's enter in this information. We put in 19 dB. We put on our distance at 1.5. As we see here, what that has is that has a dramatic effect as far as the actual available throughput. So we then move from our data rate from 21 megabits per second all the way to 57.8 megabits per second. So as we can see here, the antenna types, the available signal strength, that is going to directly affect how much the actual data rate is between those points. So we look at this, and again, what that does is that moves our data rate from 20 megabits per second all the way to 57.8 by simply changing the antenna type. That is one of the key powers of this RF data tool, is it allows us to make modifications to the system. If that 10 megabit link was not nearly going to be fast enough, simply changing the antenna type from a lower gain directional to a higher gain directional was able to increase the actual throughput 3 times. So what we can actually do is what we're going to do is if we take a look at each one of these sites, so instead of typing it into the screen, which would take quite a bit of time, what we can do is let's take an analysis for each one of those points. So if we go from the control room out to pump site number 2, it's going to be very similar. The only difference is that we're going to change from 4 miles to 5 miles. We enter that information into our data entry keyboard, and what we come out with is there is not that big of a difference as far as signal. We see here that we only have 1.9 dB of fade margin here versus what we had on the first one, but our data throughput is actually going to be the same. We take another link. The only thing that changes between the control room and the water tank is that we no longer can use that high gain directional antenna because we have to have an omnidirectional at both of these sites. So we know that's going to affect our actual throughput. So we enter that information again into our RF design keyboard. Then we come out and it will tell us that this particular link will run at 28.9 megabits per second, giving us a throughput of 14.5. Now, if that isn't going to work, we can make adjustments to it. Say, for example, we could actually put at that location, instead of having one radio with one omnidirectional, what we can actually do is use two radios, one with the directional pointing one way and one with the directional pointing the other. Those two radios can be connected through an Ethernet cable. There are different means that we can do to increase the actual throughput. But what the idea behind this above all is we can make this analysis, we can make this determination prior to the equipment being installed. That is really the key power to this tool. So then we keep adding this information. We'll take a look at this last link. This is actually 5.5 miles going from the water tank, which has adjusted antenna height at 740 feet, to a water pump site at 15 feet. We're going from an omnidirectional to a directional. So we enter in this information, and what we do is we find out that the actual RF data rate actually comes out to about the same, that 57.8, but now we have this Fresnel zone warning. And where this is coming in at, if I kick back to the tool, I'll show you where that is actually shown on the screen. Every RF link will actually show us the Fresnel zone. And what this does is this basically already tells us, based upon the equipment, the length between those 2 points, what the height of that Fresnel zone is going to be. So this particular link was actually at 5.5 miles. And again, we're going from an omnidirectional antenna here to a directional antenna out here. But the difference is that we have a height of our repeater is at 740 feet, adjusted antenna height, and our remote is only 15, okay? We see that the Fresnel zone warning comes from the fact that over this distance, our Fresnel zone, or 60% of that Fresnel zone, is actually 32.4 feet. What will happen then is that with the equipment being at 15 feet at the remote, we have a possibility that that system will actually cause a destructive reflection off the Earth's surface. Now, will it? We don't really know that until we would go out and test it. But again, from the design side, what we want to do is we want to be as conservative as we possibly can, so we make the changes beforehand. So we've identified that we have a problem here. Well, how do we fix this? To be honest with you, it's quite simple. We know that this antenna height being at 15 feet is going to give us a good line of sight, but has the potential to cause us a problem in the Fresnel zone. So what we need to do is we need to increase our height from 15 feet to some number above 33 feet. Therefore, we know that no matter what we have here, we're not going to be slamming that signal into the Earth's surface immediately running at 15 feet. So for this example, if you increase the value to 40 feet, which I'll do over here on the screen, we simply increase the remote side from 15 feet to 40 feet, our Fresnel zone warning goes away. Now, the Fresnel zone being an ellipsoid, the one thing I will show you here while I'm on the screen is, as you'll notice, the height of this ellipsoid may be different depending upon where it sits. So for an example, if we're running a frequency of 2.4 gigahertz, what the calculation is based on is the longest point, or the point in the center. The calculation that we see on the RF path analysis is actually 2.5 feet one direction and 2.5 feet the other direction. So that's a radius of 52 feet, so 60% of that is 31 feet here, right here, very much in the center. Now, if what we're concerned with is not dead center, but actually closer towards one end, we'll see what the effect is. So if it's within 1 mile on one side And 4 miles on the opposite side, we see here that the radius is only 42 feet because we've come up the side of this ellipsoid. So 60% of that is only 25 feet. So that is the point of this Fresnel zone calculation. If you use the height that is shown here, you'll always be covered because, again, that is the worst case scenario. But you may run into a situation to where that may not be a valid carrier. And it does work this way. One of the first applications that we had done with 2.4 gigahertz was at a system not far from us in a very tree-lined area, and the two antennas were in a perfect line of sight. The only problem is that they were sitting right on top of the tree line. We did the calculations over that distance and found, quite honestly, they only need to raise it by 10 feet. The equipment was raised up 10 feet and the communication became perfect. So this Fresnel zone actually does have an effect, or has a possibility of causing an effect. Now, one of the questions that always comes up is, what is the range of this radio? For most of the time, we are fairly conservative on our estimates. We say our estimate or our nominal range for these radios is about 5 to 7 miles. Is that true? Well, where does this come from? Well, that also gives us a kind of an insight as far as where some of these very, very long distances are here, about 20, 30 miles. Because you can see here, if you then put up very high gain directional antennas at both sides, you can see that you can actually get a very, very long distance out of this. So for our example, I just wanted to see how far we could actually go. So I put in our two highest gain directional antennas. That gives us 19 dB at both sides because there's a small little piece of cable. If you run this out, you'll find that the maximum range on this is actually 170 miles, running at the lowest HT rate, or the lowest rate that radio goes at 7.2 megabits per second, or even at 17 miles for the highest data rate. Well, why don't we publish that? We've proven here that we can do it. Well, we need to look at the reality of what does that actually take. To give you an idea, to run 170 miles, we actually need a minimum antenna height at both sides of over 4,000 feet just to break the curvature of the Earth. We then need to add the Fresnel zone to that, which adds an additional 180 feet. So what is this? Well, really what we're talking about is an application from one mountaintop to another mountaintop. Could it be used? Yes, as a matter of fact, we've had some applications that have used this 2.4 gigahertz well over 60 miles, but that was the requirement of it. Were one mountaintop to another mountaintop. So the physical location is really going to dictate this range. The next thing is, even at 17 miles, we need a minimum of 60-foot antenna height just to break the curvature of the Earth. This is more practical, but then again, it's not a small height difference. So what we want to do is we want to be able to give a more realistic type distance. We want to say the distance of our radio is that if you were to put it on the roof of one building, how far can we expect it to go between theirs? So what we did is we do most of ours based upon two omnidirectional antennas. So we put up two omnidirectional antennas, have 6 dB gain apiece. We add that same calculated loss, go through there. What our practical range is then is our lowest data rate running at 1 megabit per second gives us a range of 15 miles. At the fastest data rate between two omnidirectional antennas is about 0.8 miles. So our nominal range is somewhere in the middle there, somewhere between about 5 to 7 miles. So what we want to do is we want to be as practical with these systems as we possibly can. Saying that the radio can go 30 miles, it's true, it could go 30 miles, but what does it take to actually get that to happen? That's the difference between it. So to round out today, what I want to do is kind of give you an idea that we teach this so that people can get more familiar or more comfortable with the type of system design. Because quite honestly, as you see here, this is not difficult. But the reliability of the system is only as good as the system design itself. We want you to use these tools. We want you to compare the different vendor hardware so that if you're seeing something in a specification sheet and it doesn't necessarily look correct, you're welcome to look at these tools and say, oh, okay, that's actually where the problem came in, or that's how they're making this claim. Because radio applications themselves are not difficult, but they are somewhat unforgiving to small little, problems. So the planning and the evaluation are the key towards the success. So in the next section, the next lesson that we'll be going over, we're actually going to take a look at the practical use of this RF design. This gives us the math model and analysis. Once we put this into the real world, what are the things that we need to look at? So this is what we're going to call for today, and we'll talk to you soon.